Okay, this is 6.4, page 354 in your textbook. Important that you do have your textbook or your digital textbook out so that we can follow. As you can see, it's one of the only times that I've done this, the first time that I've done this, I'm putting in copy from text, and part of that reason is there's just too much data here to put up on the board. It's just taking too long. So we're going to get the point though as we go through this. So we're reasoning about data. So it's very similar to the last two lessons that we've had, and that's where we're given a table of values and then we're given a graph, or we're asked to graph that table and then make conjectures about that data. And what I mean by conjecture, it's kind of like a hypothesis in science, if you guys are familiar with that terminology. Basically, it's an idea or it's a preposition that you're giving before really looking into the details of the problem. Okay, so it's like a hypothesis. So we're determining whether a conjecture or a hypothesis about the relationship between two variables is valid. All right, so in all the examples today that we'll see on the board, basically there's a conjecture that's given, and then you're trying to identify whether or not that conjecture is true or not. So the first one, we have information about a plant here that's emitting CO2, or atmospheric carbon dioxide. We have graphed the year versus the CO2. So this graph then would be an example of what? Because we're graphing time on the x-axis, it's an example of a
independent variable.
No, it is the independent variable, you're right, but it's called what when the independent variable is time?
Trend.
Yeah, it's called a trend. Okay, so this particular graph is called a trend. Again, the reason why is because the independent variable is time. And the question says, by 2015, will CO2 be above 385? So very similar to what we've done in the last lesson, is we need to do something. When we're deciding, we have a question that's asking about a year that's not on our graph, we have to do something with this graph to find out that information. Kevin?
Extrapolate.
Right, so we need to extrapolate this data and find out what's going to happen kind of up here in this year 2015, which is in this area. All right, so the way we do that is first and foremost we plot the graph, and then we need to do a line of best fit. We chose a line in this particular case because the data was pretty straight. Okay, I can't draw any sort of curve here because the data is pretty much in a line. So we're going to take that data and extrapolate it in this direction until we line up with 2015. Once we line up with 2015, we're going to run back to the y-axis and then read that value of CO2, which is up here. Okay. If you look in your textbook, you can see a much more accurate drawing of this on page 355. You can see if 2015 is the second last vertical line. If we run that back from where the line hits it, it's going to be around 395. 395, somewhere in and around that range. Okay, so when the question reads, by 2015 will CO2 be above 385, the question is yes, or the answer is yes. Okay, and we got that answer by extrapolating the existing data, by drawing a line of best fit and then extrapolating it.
Can't you also look at the table of values and kind of estimate?
You could kind of estimate.
It's already almost over 385 at 2004, so you know it's increasing.
You're right. The only reason I would caution you to use a table of values is because the only time it really works is if it's a linear relation.
Yeah.
This happens to be a linear relation, and the only reason we knew that is because we graphed it.
Yeah.
So I would really advise you guys to use the graph, okay, as opposed to making estimates from the tables, because you can't visualize it and you can't make this kind of identification like this. Okay, any questions with that example so far? All right. So the next example, or is this the same one? Oh, sorry, this is the same example. The only difference is that they took data from a higher resolution and they took more data points. So they did it not only by year, but they took it by month. Okay, so there's a lot of data points that was involved in graphing this. And you can see we got this graph where the points were kind of a little bit all over the place. So you can see all these points. But what they found was that there was this type of pattern from month to month. Okay, certain months were around there was the same pattern that was happening every year. It's kind of this up and down pattern. All right. which kind of makes sense when we're talking about CO2 emissions, because in the winter, maybe they're using more power, they're generating more heat to heat the plant or whatnot, so they're producing more CO2 emissions. Okay, we can see that by looking at January compared to, say, a summer month of August or September. Let's see if that's kind of the pattern that's happening. Looks like the highest CO2 emissions are in April and May. Okay, so something's happening at this particular plant in April and May where they're generating more CO2 emissions. So rather than drawing, because the data is so widely spread out, rather than drawing a line of best fit, it's more reasonable to draw a curve of best fit. Okay, because this pattern does exist. So we're following that up and down pattern. Okay, so there's actually two patterns that's happening here. One is this up and down pattern every year, and the second one is that there's this kind of general upwards tendency to the pollution, or the CO2 being emitted. Okay, so we can see that this data actually supports this data. Okay, whereas these points are averages of the year, which are increasing. These points are the monthly amounts, which average out an increase per year. Okay, so we're really getting the same results here. Okay, but the reason why we choose a curve of best fit again is because this pattern is really quite evident. Okay, and it's more evident because we know that these data points are taken per month. Okay, which makes sense that something's happening specifically during the month that's creating it to go up and down. Any questions with that one? Okay, moving on to example 2.
How would you have time, for the time axis, how would you have the year and the month on the same axis?
You can see actually in the book it says number of months since December 1998. So they're actually tracking number of months. All right. So
for 1 year?
So this just goes up. Yeah. So 1 year would be 12 months. 2 years would be 24 months.
Okay.
Okay. So that's how they managed to do it. But good question. All right. Example 2. So reasoning about outliers. So Christina thinks that people with higher incomes donate more money to charities. She collects the following data. So here's the yearly income in thousands. So this person makes $21,000 a year, and this is the amount that they donated straight in dollars. So $310 they donated. Whereas this person made $55,000 a year and donated $180 a year. So her conjecture is that people with higher incomes donate more money. And so our question is Christina's conjecture correct? So if we take this
Hello, Mr.
information...
Mills.
Hi there.
Hi, is Mark Rosati